v. Let's say the arbitrary function is v, so v is a vector. So let's draw a diagram over here. So we have this vector function here. So this is my vector function v. So this depends on x, y, z. So and we have the line integral here. So from this point to this point, let's say a to b. These are my points, and we are considering a small displacement vector here. So this is going to be my infinitesimal displacement vector. So let's say that dl. So this is my infinitesimal displacement vector. So I'm going to define the line integral. So the line integral is defined as integration of a to b. Since we know that v is a vector function, so it depends on x, y, z. So now we are going to have the dot product with dot product with the dl, that is the infinitesimal displacement vector. So we are going to have this dot product of these two vectors. So when we get this dot product, we are going to get a scalar here. So we have to integrate in between a and b, because you know that if we consider only infinitesimal displacement vector, we have to integrate this whole to get the line integral. So there's a special condition here. So if this b point lies on the a point, what happens here? So that means that the point is coincides. So that means, let's say a is coincide with b, that then we can say that this forms actually a closed line. This forms a closed path actually. So for a closed path, we can say that the line integral, the definition, by the definition we can say that actually there is a symbol for this kind of a line integral. When we have a closed path, we are drawing a circle around this integral symbol when we have a closed path. So if a coincides with b, then we have a closed path. So it can be represented by drawing a circle on the integral symbol. So we have to calculate the v dot dl on the closed path when we have a is equals b. Okay, now second we are going to look at the surface integral. So in order to look at surface integral, I'm going to draw a surface over the vector field. So this is my vector field v, and I'm going to consider a surface S here. So I'm going to draw a small patch of area vector. So this is my small patch. So let's say dA. So you can draw a vector which is perpendicular to this infinitesimal surface area patch. So that is going to be dA vector. So this is always perpendicular to this patch. So actually this patch is drawn on the surface. So now we have a vector function, and v is a vector function, so you can say that now dA vector. So dA vector is the infinitesimal patch of area vector which is perpendicular to the surface area dA. Surface area dA. So this is my surface area, infinitesimal surface area. So this is going to be the infinitesimal patch of area vector which is perpendicular to the surface area vector. So which is perpendicular to the infinitesimal surface area. So now I'm going to define the surface integral. So when we have a surface, so I'm going to define the surface here, so that's why I wrote S here. So when we have a surface integral, that means that we have to have v dot dA vector. So dA is the infinitesimal patch of area vector which is perpendicular to the surface area dA. So this is actually a double integration. So that means you have, when you have a dA, that is a surface area vector, so that means you will have just like if you have a Cartesian coordinate system, you will have dx and dy. So that means you will have to integrate 2 times with respect to x and with respect to y. So this is the basic definition of the surface integral. So now finally we are going to look at the volume integrals. These are actually similar things, but you will need to know these things. So if t is a scalar function, the difference between the difference between the volume integral and the other integrals, that means the other integrals means we have considered line integral and the surface integrals. So compared to both of them, volume integral is different, because when it comes to volume integral, we are considering a scalar function, but in the previous integrals we have discussed about the integrals using vectors. So now I'm going to get my scalar as t. So now I'm going to add another term. This term is called as the infinitesimal volume element. Infinitesimal volume element. So now I have 2 terms here. One is a scalar function and the other one is the infinitesimal volume element. So in Cartesian coordinates, you can write this infinitesimal volume element as dx, dy, dz. So now I'm going to have this kind of box. So you will have dx here, dy here, and dc here. So you will have this dx, dy, dc. So now you have to integrate 3 times to find the volume integral. So now you have over volume, so you will have t function here and d tau. D tau is the infinitesimal volume element. So let's say that the small element is d tau when you have a volume. So likewise these gives forms everywhere on the volume. So you mean that you have to integrate it to find the total volume of this volume integral. So that means you will have to find the triple integration, because you know that from the Cartesian coordinate system we can write this infinitesimal volume element as dx dy dc. So since we have dx by dx dy dc, so it's going to be a triple integral. So when you are given with a scalar function of let's say for an example x y c, so you will have to integrate this 3 times with respect to x, with respect to y, and with respect to c. According to the coordinate system that you use, these things can be changed. So I think you have understood the integrals. In the next video, I'm going to talk about the fundamental theorem of gradient, fundamental theorem of divergence, and the fundamental theorem of curl.